This is not a tutorial. There's a whole bunch of packages here. I'm going to give you like a super brief example of what each one does. The goal really is to help you choose the tool that is the right thing for you to use in your work. Before I start, I want to point out one thing to distinguish my personal recommendations, which I plan to give you some of. I've formatted my personal recommendation slides like this. There's a little speech bubble in the corner. That way you can know what is my opinion and distinguish it from the real sort of factual information, which I hope is mostly correct. So that's a grain of salt. So take one of those when you see the speech bubble in the corner. So to help you decide whether you want to take my advice, I'll just tell you a little bit about who I am. I've been writing code for a long time. I think I still have my first Python script. It ran in Python 1.4. I used to work in physics. Now I work in finance at Tudor Investment Corporation. In physics, I wrote a ton of Python data analysis code. In finance, I still write a ton of Python data analysis code. A lot of it involves dates and times. This is useful in science, useful in finance, useful in a lot of places, as you may imagine. My GitHub is Alex8Samuel. If you go there, you will find a lot of half-finished projects that you've never heard of that are languishing. So you have nothing else to do. So before we launch into the specific packages, let's start with some preliminaries, so just some basic concepts. So what is time? I'm not going to get super philosophical here, but I think for the purposes of this talk, we can think of time as, it's kind of like space, except it has one coordinate instead of three. It's pretty simple. It's kind of this line, and numbers and time kind of grow monotonically. It's a fairly straightforward concept. It's actually easier than space. And in computer programs, I think what we're usually interested in is recording the exact instant when something occurred. There are a lot of different things you do with time, but I think this is the most common application. That's probably 90% of what you care about. Something happens like a log line was recorded, or the user performed an action, or a transaction occurred, or something like that. And you want to record when this happened, so you can kind of think about it and process it later. Now, humans, of course, have to go in and complicate the situation. It's a very simple concept, but humans make it very complicated. So one way we do this is that we divide time into these roughly 24-hour spans called days, which kind of correspond to the rotation of the Earth. And then we specify time as a date, which is some coordinate in this count of 24-hour days. And then once we know which day we're talking about, we talk about the time of day, which is starting from the beginning of the day, which we call midnight traditionally. We count some additional amounts of time elapsed. So we kind of have this double hierarchy of coordinate systems. But even with days and times, we have this completely bizarre coordinate system. Every SI has kind of cleaned everything else up. But with time, we're stuck with years, 12 months to a year, 27 to 30 days a month, 23 to 25 hours a day, 60 minutes to an hour, and then 60 seconds to a minute. So this is a very obscure a time system, which unfortunately we all learned in kindergarten, and this is really the only natural way we as humans think about time. And then to complicate things even further, we don't even agree on when the day starts. So each government is entitled, as a government, to slice up its territories into time zones, which here's a map. This is probably not even current. So I just took it randomly off Google image search. So each government can go and slice up its territories into these time zones. Within each time zone, we agree to set our clocks forward or backwards from some hypothetical time zone, which we call UTC, by some amount. So then all of the clocks in the time zone are set the same offset from UTC. But that offset isn't even stable throughout the year. So we have daylight savings time when all of the UTC offset shifts for a particular zone forwards or backwards. And then to make things even worse, governments are at their liberty to change the time zones anytime they want, which they do. So it's not even consistent over history. So these are the problems that we have to deal with time. Time itself is not super complicated, but dealing with all the nonsense that humans have layered on top of it is really what most of the time processing code is about, unfortunately. So with time zones, fortunately, the selfless souls at IANA maintain a database of time zone data that lists all of the different time zones, their historical, current, and projected future offsets from UTC as a function of time. This is often called the Olson database. You may have heard that term. On most Linux systems and Mac OS, it's installed in a directory called user share zone info. If you've never looked at this before, CD there and poke around. There's a bunch of files for different time zones and symlinks as well that contain these data sets. On Windows, it's stuffed in a DLL. I'm not a Windows guy, but this is what I tracked down. So it's a little bit harder to look at. The time zones in the Olson database have geographical names. We are right now in one called America/New York. They're named generally after a continent and a city, a major city in the time zone. So right now, New York happens to be UTC minus 5 hours because it's wintertime. In summertime, as you probably know, we're on daylight savings time, and that's UTC minus 4 hours. But I want to point out that UTC minus 5 is not the same thing as America/New York, which is also not the same thing as US Eastern. For example, there's a time zone called America/Bogota that is also UTC minus 5. And in fact, they are UTC minus 5 all year long, whereas we switch between UTC minus 4 and UTC minus 5 because they choose not to honor daylight savings time. So I'm just kind of laying the groundwork here of all of the kind of complications that this software is supposed to deal with to motivate it. Now we have countless variations on how to format dates and times. I just picked a few random ones here. You can have times, days and times with or without the UTC offset. You can have dates, slashes, colons, commas, all the punctuation you can imagine. Some people put the year first, some people put the month first, some people put the day first. You can have names of months, numbers of months, abbreviated names of months, days of weeks, abbreviated days of weeks. And of course, it doesn't have to be in English, right? Every language has its own conventions and names for all of these things. So this is super fun if you have to work with internationalized user interfaces. Anyone here do UI, internationalized UI? All right, so I hope you never have to do this. For computers, there is a standard family of formats called ISO 8601. It's a long, boring spec that tells you all the different ways you should format date times for use in computer programs. This is not for human users. This is for computer-readable, stringified dates and times. But ISO 8601 actually is a family of formats. There is on top of that an RFC 3339, which specifies a specific format, or maybe a much smaller family of formats, which is recommended for internet protocols. And those look like this ones at the bottom. There's a date separated by dashes, a capital T, the time, and then the UTC offset at the end. Sometimes actually instead of +0, 0:00, you'll just see a Z. Z stands for Zulu time. This is an army time, old convention. And that also indicates the UTC time zone. So if you see a time zone ending with Z, that means that is a UTC timestamp. So that brings me to my first recommendation, which is to use the RFC 3339 time format in all of your APIs and in your data files. If it's for non-technical human consumption in the user interface, by all means, internationalize it to whatever the users want. But when you're working with code that's mainly for developers or for the computer itself, use that standard timestamp. Your code will be more compatible, your data files will be easier to read in other systems, and you will save yourself a lot of implementation nuisance. Okay, I haven't said anything about Python yet, so let's go on to Python now. So I kind of spent a long time serving a lot of the different packages out there, and I found 4 general categories of ways that people represent dates and times in Python. The first one is not even a bunch of packages, it's just using built-in types, so strings and integers. You've probably all done this before at some point. The second one is the standard library datetime package. So that ships with Python. It's there as soon as you install Python. You don't have to install anything else. But there are also a sort of ecosystem of helper packages that are used with datetime to fill in some of its feature gaps. So that's the second category. The third one is there are derivatives of the datetime library. People have taken the datetime library as a starting point and use it to implement sort of richer or easier to use datetime libraries. And I'll talk about some of those. And then finally, there are representations for dates and times that are specific to large data sets. So if you have, rather than a single time or single date, you have a column in a table or in a large data set, there are representations that people use for those as well. So I'm going to go into each of these. First, primitive types. I won't belabor this too much, but a simple way to obviously specify a time or a date is a string. So there's some of the stringified formats. You can take my advice and use RFC 3339, or you can use something else. Another option is that you see often for dates, people will take the integer components of the date and encode them in one single integer. How many of you have written code like this at some point? Come on, admit it. I've written it at least 20 times in my life, easily. So that's super convenient, and these have one huge feature, and that is every single system can store a string and can store an integer. So you have a CSV file, you have a JSON file, you have some ancient database, whatever your system is, you can stuff this in. Right? And that's a super useful thing. You don't have to worry about what kind of dates does it support, was its resolution, stuff like that. You just drop the string in there, you'll get it back. So that's fantastic. But if you have to do any operations at all on these times, you're completely on your own. Right? You have to implement everything from scratch. You want to know what the year is, you got to fish it out. You want to know what the next date is, you have to know how calendars work, right? So you have absolutely no operations handed to you if you use these formats. So my recommendation is to avoid these, except for very simple formats like CSV and JSON where you have to, right? They don't provide date types, they only provide strings, or I guess JSON has a few other things, but dates and times are not among them. So in these cases, put a stringified date in, but in other cases, I strongly urge you against using stringified and particularly integer encoded dates and times in your applications. Because as soon as you need to do any operations at all, you're stuck and you end up reinventing the wheel. There's another type of integer representation actually that are slightly better. These are tick representations. So in a tick-based representation, you choose a starting time, which is called, for whatever reason, an epoch. And then you choose a time unit, let's say a second. And you just count ticks starting from that epoch, or negative if you want to use negative integers. So in Unix and in Python, traditionally we use UTC midnight on January 1st, 1970 as the epoch, the starting point. And then we count seconds forward. So this has a very simple physical interpretation. It's very clear. It's very simple. The simplest Python date API actually is this one. It's the time.time function. And this returns your computer's system clock in seconds since midnight, January 1st, 1970 UTC. So if this representation was good enough, this would be my last slide and this talk would be over and the world would actually probably be a happier place. But this is not the case, unfortunately. So the sort of thing that most people reach for first is the datetime package in the Python standard library. So if you import datetime, you already have a lot of functionality there. This solves many of our problems for us. The datetime provides a time type, which it calls datetime. So both the module and one of the types in it are called datetime. So just to disambiguate, in the talk, if it's in monospace, then it's the class, the type name. If it's in regular font, then it's the package name. So the datetime type in the datetime package stores a time. It stores year, month, date, hour, minute, second, microsecond components under the hood. So there's a little data structure which stores these components in it, but it provides all the operation, not all, it provides many of the operations that you would want on top of it. Because it stores microsecond pieces, the resolution is 1 microsecond, which may or may not be enough for you. People who work in finance may not find this adequate. Some technical users may not find this adequate either, but for things like Apache logs or whatever, it's probably enough. It also provides 2 flavors of times, and this is an important distinction. This is terminology that I think is Python specific, but is very widely used. There are the notion of naive date times, which do not carry a time zone. They only carry a date and a time of day. And then there are localized time zones, which contain a date, a time of day, as well as a time zone. And I just want to point out, a naive date time does not actually specify the instant when something happened. If I tell you this happened at noon on November 11th, 2017, you don't know when it happened because I might be talking about New York, I might be talking about Tokyo, I might be talking about London, I might be talking about Timbuktu. You don't know, right? You need either a time zone or a UTC offset to turn that date and time into an actual physical time when something occurred. But sometimes in some software that time zone or that UTC offset is implicit. So it can get tricky. One thing I will point out about datetime is even though it stores all of the components for each datetime, the class is implemented in C and is actually rather efficient. It's actually surprisingly fast given how it operates, which I found surprising when I benchmarked it. Here's some quick examples of some things the datetime library will do. You can call, for instance, UTC now. You get back the UTC current date and time. You can fish out components, .year, .month, .day. You can split it into a date and a time. And then there's also parsing and formatting, which is based, if you've worked in C, there's C library functions called stirftime and stirptime that have been around forever. And they have these like %m, %y, %d, %h format codes that are used to specify how you parse in a datetime string or format one back. So here's an example of that. It is nicely integrated into Python's standard formatting system. So for instance, you can see in the second line from the bottom, you can put those format codes directly into the curly braces in a string format. So that's a super useful feature if you're formatting these. But these %h, %m things take a while to get used to. You kind of have to go stare at the table and find the one you're looking for. And after 5 years of writing this code, you'll finally remember them. So my advice is to represent a date, use a date object. So datetime gives you a datetime, which is a date and a time. It gives you a time of day, which it calls time, and it gives you a date object. And use the correct one for the job. If you're only talking about a date, don't put in a midnight time for a date, because a day and a time, an instant are not the same thing. A date time and a date are not the same thing. A date represents a geographically specific, roughly 24-hour period, whereas a date time represents an instant, hopefully a localized one, so you know which one you're talking about. Some shortcomings of datetime. It has some limitations. One major one is it provides a time zone API, but it doesn't actually provide any time zones. So there's something called TZ-info, which is an interface for what time zone information should look like, but there are no actual time zones in datetime. The API also is not always the most convenient. If you work with it a lot, you'll kind of learn your way around its idiosyncrasies, but it takes a little while to get used to it and to implement some more complicated operations. And finally, I would say that the 1 microsecond resolution is actually a showstopper for some applications rather. So you have to decide whether 1 microsecond is an adequate resolution for you. So one way people get around this is they build libraries around the datetime package. So one of them, well known, you probably have used it, is called PyTZ. This contains its own copy of the Olsen database, so you actually have to update it regularly to make sure you pick up the latest time zone data, even if the interface doesn't change. And it implements the TZ-info interface using this data set. So here's an example of how you use it. One thing you have to be very careful about is that with PyTZ, you have to call this timezone.localized method on your naive datetimes to turn them into localized datetimes. That is the correct way of converting a naive datetime to a localized datetime. If you just try to stuff the time zone object into the TZ field, you will get the wrong results. And this has screwed up lots of people many times. So take this code and kind of study it if you plan to use PyTZ. My recommendation is in your code to use explicitly localized UTC datetimes as much as possible if you use datetime and PyTZ. So my personal version of now looks like this. I call datetime.utc now, and I immediately will localize it with pytz.utc. So you look at now the return value from that. It says tz-info equals UTC at the end. I know this is a UTC datetime. Any other code that tries to manipulate it is forced to recognize this as a UTC datetime. Another option to use with datetime is a package called dateutil. Has been around for a long time. It also contains a time zone implementation in dateutil.tz, and it not only carries the entire Olsen database with it, but it will also use the one installed on your system. In the old days, that used to be a bad idea because a lot of older, especially Linux distributions, did not have up-to-date time zone databases, but I think this mostly has been resolved in modern distributions. So chances are, like my laptop has one that's about 2 months out of date. My Linux computer at home, Ubuntu 17, is also up to date. So this is not really an issue. One other thing dateutil provides, which is pretty nice, is convenient parsing. So you'll notice that on this parse line at the bottom, I handed it some random datetime format that I happen to have, and I didn't have to tell it what the format was. It kind of looked at the string and decided, oh yeah, that looks like a date up front, November is 11, and it produced the correct datetime out of it. So, and it even localized it. You see that TZ-UTC at the end. So that's a useful feature. There's some other stuff in dateutil. I'm not talking about calendars and recurrence relations at all in this talk, but if you need that stuff, dateutil is a place to look. I'm not going to go into that here. Another thing is it has an Easter calculation. If you want to be a time nerd, look up the Wikipedia article on Computus, which is a multi-century long mathematical history of ways to calculate the date of Easter, which for some reason is complicated. So it's kind of interesting if you have a Saturday afternoon to waste. Babel is an internationalization library that has date and time support. So if you need your date times in Chinese, this is one way to do it. It has a fairly wide range of languages. It also supports, if you don't like the %y, %m, %d stuff, it supports a more sort of JOTA style datetime formatting where you put MMMM and YYYY and things like that. So if you prefer that, you can consider using Babel. But the main advantage is that it knows lots of languages. One last one I want to, actually second to last one I want to mention to go with datetime is this package called udatetime, which is basically an acceleration library for a handful of operations inside datetime, particularly for parsing and formatting strings. So if you, for instance, are writing log files really, really fast, and all you need to do is get a stringified UTC datetime as a for a timestamp to go in your log files, you can consider using udatetime. It's substantially faster than the core datetime implementation. I think this doesn't run on Windows. I think it's POSIX only. And finally, to go with datetime, there's a nice package called Humanize. This is, you know, like when you git push and you go on GitHub and it says, oh yeah, you know, Alex Samuel committed this 4 minutes ago, right? It kind of knows, it knows when this was committed, it knows the current time, and it writes a sort of human-friendly indication. And then if it was yesterday, it says yesterday, and it may say a week ago or 2 months ago. That's what Humanize does, basically. So you can see here, I took the current time, I slept for 10 seconds, and I asked Humanize to format it, and it said 10 seconds ago. If I had slept 20 seconds, it would have said 20 seconds ago. So that's a fun thing for user interfaces. Now, on to derivatives of datetime. There have been several attempts to improve datetime either by wrapping it or extending it. So let me present a few of these. One that's been around for a while is called DeLorean. So this wraps datetime.datetime in a pure Python wrapper called DeLorean. And it also integrates PyTZ, Babel, and Humanize. It provides some convenience methods. So one really nice thing about it is you don't have to instantiate your time zones explicitly. You can just pass in a time zone name, and it figures out how to fetch the time zone for you. And it has some stuff like truncate. As I said, it integrates Humanize. One thing I don't like about it is it provides no date and time classes. It only has the datetime class. And the API sort of feels inconsistent to me. It doesn't, for instance, participate in the normal Python string formatting. You have to use the specialized format datetime method rather than normal format. Another option is Arrow, which also wraps datetime.datetime in a pure Python class. As with DeLorean, you can pass in time zone names. It integrates dateutil.tz for time zone information, but also it does not provide date and time classes. It only provides the datetime type. But it does have some nice, well-designed convenience methods. You can convert a lot of things very easily to an Arrow instance. So here I passed in epoch seconds, that 15117, and so forth, and immediately figured out what this is. It has methods, for instance, to replace components, to shift forward or backward, a month, a day, an hour, whatever you need. And it actually also has its own implementation of customized datetime formatting in about 50 languages. This is 1 month ago in Hindi, so tells me Google Translate. I don't actually read Hindi. But if you can get that Humanize thing for humans and who don't speak English, which is kind of nice. And then the third derivative of datetime I want to talk about is called Pendulum, which is a very ambitious extension. It not only extends datetime, but there is an extension of the time class, an extension of the date class, and of tzinfo and time delta. It is the only expansion package that provides all of these types, not just a datetime type. It only supports localized times, which I think is a feature, not a bug. It doesn't let you use naive datetimes. And because it doesn't actually wrap the types in the datetime package, it subclasses them. That means its types are drop-in replacements for other APIs that may require a datetime or a date or a time type. So that's a very handy feature as well. It uses time zone data from yet another Python package called PyTZ data, which only includes the data. This has its own implementation of reading the time zone files, which is some weird binary format, which you don't want to implement yourself. So Pendulum has smart parsing. You can basically hand it like datetime. You can hand it some random timestamp string that you pulled off the internet in some CSV file, and it can figure out how to parse it for you. It has lots of formatting options. It supports the percent style ones as well as the JOTA style, YYYY, MMDD style. It has about 50 languages. This is what dates look like in Turkish, I think. And has a ton of convenience methods. You can say, convert this, find the start of the century containing this date, or the end of the, you can find me last Wednesday, find me the end of the hour. You can add hours, add minutes. And so this one, I think, is the most feature complete of all of them. And the API, in my opinion at least, is pretty nicely designed. But this is PyData, so one time value is clearly not enough. Everyone here probably has 1 million of them at a time, minimum, that they need to work with. We want to store data sets containing times, containing dates, containing times of days. So let's consider the options. And there honestly are not that many. If you use NumPy, you are probably familiar with datetime 64, which is a D-type that NumPy provides. There's actually a family of D-types. It's parameterized by a unit, which is, I think, unique in NumPy D-types. It has the advantage of storing times and dates very efficiently. It has the disadvantage that there are basically no operations you can apply to them. You can put a time in and you can get it out. And you can convert it to other time units. That's about it. You can go from seconds to microseconds, to days to nanoseconds, but that's basically it. And I think you can compare them, which one's larger than the other. So here's an example of that. I took some times and I told it datetime 64 nanoseconds, and I get an array of nanoseconds. And this is fantastic because they take up 8 bytes each instead of 400 bytes or whatever a big object takes. So if you have 1 million of them, you care. However, Pandas, now Pandas is probably what most people use for data science. It's backed by NumPy arrays, so Pandas does use datetime 64 under the hood, but Pandas goes through great lengths to paper over the feature gaps in NumPy's datetime 64. It's really a heroic effort. So it uses datetime 64 under the hood, but one of the things it does is it adds localization. So if you have a pandas datetime index, sorry, it's kind of hard to format code to fit on in a big font on the screen, but if you have a pandas datetime index, you can call tz localize on it and give it a time zone string, and you'll see pandas now has crammed the time zone into the d-type, which NumPy doesn't know anything about that. This is a pandasism, but it's super useful. So datetime indexes then have a bunch of time-specific methods. I see people yawning. I told you this would be boring. TZ convert, for instance, which will convert from one time zone to another. This is the kind of thing. It's super boring until you need to do it, and then you're like, holy cow, how do I do this, right? So it's really good that Pandas has worked so hard to add this stuff. If you have a time-valued series, so where not the index, but the actual values are times, the time methods are not directly on the series object. There's this DT proxy object that kind of collects them together. So you do series.dt.tzconvert or tzlocalize, or just .hour if you want to get the hours out. And that's how you work with time-valued series or columns and data frames. One other thing that Pandas does to take heroic efforts to make your lives better is it provides this timestamp class for single values. So if you have a NumPy datetime 64 array and you fish one value out, you get back a datetime 64 scalar, which has as many operations as the array does, namely nothing. But Pandas instead gives you this timestamp object, which derives from datetime, but also does a bunch of things. First, it patches it so that it has nanosecond resolution instead of microsecond resolution, which is super useful. And then it tosses in all of these other datetime-specific methods that are available on the series and on the datetime index. So if you take this datetime 64 column and fish a value out, and you get back this weird timestamp class, that is Pandas trying to be helpful. If you go to the underlying NumPy array and get a value out, NumPy is not going to help you. So those are the packages I want to talk about. We're running out of time, but I want to talk briefly about performance. I don't have time to present benchmark results here. If you go in the GitHub repo, some of the results are there. You can obviously run your own. The usual caveats about micro-benchmarking interpretation apply here, but I just want to give you a general sense for performance of these things. As I mentioned before, the datetime package is surprisingly efficient. A lot of operations run in under a microsecond on my laptop. Compared to that, udatetime provides a few things that are about the same speed or faster, but probably is not going to be a big deal for most people. NumPy's datetime 64 and pandas timestamp operations are generally a little bit slower for scalar objects, but in an array or in a series or in a data frame, they're quite fast. DeLorean, Arrow, and Pendulum add a lot of overhead to time. So if you care about performance, these are probably not for you. DeLorean particularly is kind of super slow. And then among the time zone libraries, PyTZ seems to perform faster than dateutil.tz. So if you have a choice, probably PyTZ is the way to go. Finally, roundup. There's some more stuff. Again, in the write-up, there's a feature matrix. You can see all the stuff in a grid. But my recommendations are, for ease of use, if you're working with individual times, dates, or whatever, Pendulum, I think, is the best choice. It has a ton of features. The API is clear. The documentation is good. In contrast to DeLorean and to Arrow, it provides date types, time types, and so forth. And as I mentioned before, its classes are subclasses of the standard module ones, so they're more compatible with other packages you may need to use. I would say Arrow is a solid second choice if you don't care about date handling, because it doesn't provide a date type. DeLorean I can't really recommend. I think it's somewhat older and hasn't been developed much. If you care about performance for individual values, stick with datetime, the built-in datetime, and use PyTZ for time zone data. The feature set is somewhat sparse, but as I presented, you can augment it somewhat with some additional third-party modules. And for large data sets, I can't really recommend NumPy unless you are fully committed to NumPy as it is. It'll store your date times, but that's about it. If you need any other operations, go with pandas. And finally, my last bit of advice is that even if you are using pandas primarily, I recommend you learn how to use the standard library datetime class. It is the sort of lingua franca of times and dates in Python. So a lot of APIs which are not data science oriented may force you to use it. So you should probably learn how to use it. That's it. Thank you. So questions? It's actually better than that. Olsen databases are not snapshots of current time zone rules. They have complete time histories since actually pre-atomic clock days so like for instance, it has a notion of what the average US Eastern time was in the year 1900. It actually knows the time history and some prediction of the forward future of time zones as governments provide them. So remember before I said you have to use this TZ localize to convert a naive datetime to a localized datetime. What that does is it actually looks at the datetime and figures out what time the datetime is looking for and uses that to find the right point in that time zone's history and provide the right offset based on that. So it's done for you. Those guys are really like dedicated. The data set behind this is crazy detailed, and there's lots of weird geopolitical stuff going on under the hood. More questions? I had a chat sort of about that with a certain pandas maintainer who's in that corner of the room. We can chat with him afterwards. I think I can't speak to that. Anything else? I know it's fast talk, so look at the write-up. It's kind of easier to read, actually, than to listen to me blather on. So thanks very much.